Hello everyone, welcome to part 2 of the video by Flat Earth and Coffee. I want a coffee now. What are the odds heliocentrism is statistically impossible? Last time we have talked about how he is not bothered to read up on any of those numbers and thus called them impossible because either he doesn't understand them or he hasn't researched them far enough and thus they seem, I guess you could say, impossible? Yeah.
What about, here's another statistical impossibility, the size of the sun and moon in relationship to each other? Well, science will tell you that.
Again, this is not a statistical process, so it's not a statistical impossibility because they have nothing to do with each other. But I think this is the only point where I will give you, it is a coincidence, a surprising one, that the sun is roughly 400 times, or that the angular size of the sun and the moon are roughly the same in the sky. Now, they are not precisely the same. There are eclipses, for example, where you can see the sun, a ring of the sun around the moon. There are eclipses where the moon covers more than just the sun, which obviously then we don't see because, you know, we don't see the sun. But this is very rough. This is not perfect at all.
The sun is 400 times bigger than the moon, but it just happens to be 400 times farther away.
On average.
What are those odds that it's 400 times bigger? Not 401, not 389, but 4.
I mean, in all fair, again, it is on average. It's not always. You have seen I think they're called annular eclipses before, right?
400 times farther away. That is impossible, right? But you have to believe that, and that is science. That's why I added this slide, because that is what physics teaches, right? As it happens, even though the moon is...
I'm sure if you read that article completely, they would mention that it's not perfect all the time. I guess you didn't. Actually, you know what? Well, why not have a look? Did he link? No. He linked every flat Earth thing that he has, but he didn't link to any of the sources, which is a big surprise. Let's have a look. Why do the moon and the sun appear to be the same size in the sky? Why do the moon and the sun appear to be the same size in the sky? Okay, I don't get the IOP article there. Why is my screen white now? I don't know. Now go away. Go away, cookies. So, oh, okay. This is kind of a. This is a. I see. This is not an article. This is kind of a overview of all of these questions. Well, okay. They don't give the answer here. Credit where it's due. But you can if we remove the IOP here again. My screen turns black. I don't know what's up with that. I'm sorry. No. Oh, Hertfordshire. That's pleasant. I was there at that time. No, I was home already when this article was written. I visited. No, wait, hang on. No, I still was in Hertfordshire when that was written. Oh, that's pleasant. Actually, I was there when they wrote this article. About important, right? Hasn't always been the case, by the way, just saying that. Yeah. And he even talks about annular eclipses. So, yeah.
400 times smaller than the sun. It's also about 400 times closer. Now, they just did the inverse explanation of that, but stating the same exact thing. And that is how we can get this, a solar eclipse, when the moon supposedly passes in front of the sun.
Those cases exist, yeah.
And we see this black out of the sun that is perfect, right? In their dimensions, they are the same size. Yet one is 400 times bigger. Or maybe, just maybe, they're the same size.
That's the only thing where I kind of don't have anything much to say apart from, well, it is how it is. We know that they are definitely not the same distance from radar measurements, for example. But that's the only point where I say, yeah, it's just coincidence. But you're bound to stumble across some coincidences, right?
What about a sorrow cycle?
Hey.
I think that's statistically impossible. So easy, a Babylonian can do it. A sorrow cycle is an 18-year cycle, which has continued perpetually since being discovered by the Babylonians. Right, this is, you can see that you can look this up. This is from Encyclopedia Britannica, but NASA has articles on it as well. You can still use a Saros cycle today. They are still accurate. This was the Babylonians are
Why don't you tell us what they use it for?
credited with it going back to 500 BC, which would make it about 2,520 years old. That means Saros cycle, this 18-year cycle, has been going on for 2,520 years.
Within error. It's approximal, you know.
Perpetually. Perfectly.
Citation needed for the perfectly. It's completely sufficient for this kind of cycle to be accurate within a couple of hours. And that's absolutely what we would expect it to be.
With precision, as we're rocketing through space, spinning, orbiting the sun, shooting.
Did you look at any of the numbers that would make you understand better why we still see it? I bet you didn't.
To the cosmos, 1.2 million miles an hour, right? What are the odds of that? It's impossible.
Not a statistical process again, thus the question is completely devoid of any sense.
All these impossibilities stacked on impossibilities, stacked on...
The moon isn't perfectly spherical. Where do you have that from? That's just not true. The moon isn't perfectly... I think there are like 2 kilometers... the diameter of the moon, or the radius, I don't know, is like a couple of kilometers different from the polar radius to the equatorial radius.
It just can't be, right? What about the perfect sphericity of the moon? The moon is a perfect sphere. How did...
Citation here, you can even see on your own picture that it's not perfectly spherical. I can't. Did you see these little notches here? Circles don't have notches, in case you didn't know, which apparently you didn't. Maybe no one ever told you what a circle is.
How did that happen? How did it get chiseled down in space where there's no friction whatsoever?
Chiseled down. It's called... Oh god. Okay. Planetary bodies turn around, or roughly spherical, just from gravity alone, because the rocks or the material in general in the center of a planetary body gets squished by the weight of the material above it, and the bigger they get, the better they are kind of approximating a sphere.
However, where did the moon come from? Why is it perfectly...
That's a good question. We currently believe that the moon came from a collision between something that was roughly Earth size, or like the early Earth, and the collision with something that must have roughly been the size of Mars, which ejected a whole bunch of material, which accumulated and formed the moon. This is our current best understanding.
Spherical. Why is there no hotspot on it as well?
Oh, come on, the old hotspot thing, please. Oh my god. The hotspot, or the way that planetary bodies are illuminated, relates to 1, distance, 2, the makeup of the surface, and 3, the size of the source of the light in relation to the surface. Yeah.
But what about the phases of the moon? The phases...
They kind of bear no relevancy, but...
are another statistical impossibility. That is...
Why is it the moon has phases? That's impossible. That's your argument. Come on.
We see the same phase continuously. It has never changed.
That is not true. The Babylonians recorded a different... Since you have been talking about the Babylonians earlier, they recorded a slightly different period in between lunar periods, actually. Also, the 29.5 is an average. I believe in some cases it can be like 30, and I believe in some cases it can be like 28 days, although I could be wrong. I'm not a big thing on a big expert on the moon. And perpetually citation needed.
29.5 days, according to science. This phase is...
Citation needed, according to you. Not according to science. Don't lie.
Perpetual and never changes. All of these things, there's so many statistical impossibilities, and all of these things are all happening at the same time, all stacked on top of each...
Not a statistical process, once again.
other. We're not going to...
Do you know what a statistical process is? Or like a statistical anything? Because I don't think you do.
Play the whole thing, but you get the point. We've only ever seen one side of the moon. What are the odds of that? Exactly 50%.
No.
Unless you believe in... We went to the moon... we went to the...
Oh my god. Okay, well that was funny. The chances Again, because this is not a statistical process. We only see one side of the moon because the moon is tidally locked. I have explained in a previous video that tidally locking is a phenomenon that can be derived from physical processes of how objects that are in gravitational interaction with each other that are made up of like non-ideal materials will cause torque on the other body, and thus over a long period of time getting them into tidal locking, which has happened with the moon and Earth.
Moon, and this is a photo from Apollo 16 where they were able to get a picture of the backside of the moon. Wow. If you believe that, I feel sorry for you. Here's the
I do feel sorry for you though.
front of the moon. Look at this. There's the front. Why is the back, if you believe in this, why is the back why are the craters so much more pronounced? Why are they so much deeper?
This has to do on the one side with, first of all, if you would make such a comparison, you would need to pick the same camera, because the first one was clearly different from the second one. Just because one camera, the settings may pronounce shadows or something. But you are correct. The far side of the moon has more craters than our side of the moon, I guess. This has to do with the material makeup, because on our side we have more basalt, and basalt is harder than the things that you see, so you can see small craters a lot better on the far side of the moon. It also has to do with Earth's gravitational field, where one imagine an asteroid comes from roughly the direction that Earth is in. It will be significantly deflected by Earth. If it comes from the other side, it will just be it just goes on straight, right? So the moon is protected in a sense on one side, on the close side of the moon, from asteroids by Earth's gravitational field. Also kind of Earth is in the way, if you will, but that's only a very, very small angular size, of course, so that won't play a big part.
Are they implying that the back is getting hit harder, or like the front's
more often
front's protected by the Earth or something like that?
Yes.
I mean, the moon's supposedly 236,000 miles out. There's
not because of the distance though, because of how asteroids are deflected in gravitational fields.
It can be hit by all kinds of angles. And if it were being hit more so, or by bigger objects in the back, if the front is being protected, wouldn't one of those cause it to spin? What about orbital?
What do you mean cause it to spin? How much mass or how much energy do you think an asteroid has? Very strange statement.
Periods, the perfect timings of the planets.
Oh god. Before you say anything, I don't know what this is about. I have, while skipping through this video to determine whether or not I should make a video about it, I have very, very previously watched a section from a brief part from this section where he's talking about Venus, and I can already tell you his argument here is the orbital periods of the planets don't change, which is wrong. I love it. Oh god.
Mercury has an 88-day orbital period.
It's almost 88 days. I think it's like 87.97 or something.
88 days perpetually. 88 days. This is another clock unto itself.
It changes over time though.
Its own timepiece, telling its own time. It is on a perpetual 88-day circuit. What are the odds of that? With all these tugs and
this one, I saw this one briefly.
Pulls of gravity going on, right? And movements, and how do we get?
Again, no statistical process. The question what are the odds is completely misplaced here, and the rotation of the orbit changes.
Yeah. Why does Venus have a 225-day perpetual orbit? Why does Mars have a 687-day perpetual orbit? We can measure this again and again and again. Why does Jupiter have a 4,333 in place and have a 10,756 Earth-day orbit? Never make
he goes through all of these planets now and says,
NASA, a lot of those work from
possible.
NASA. Basically, NASA dictates the science. NASA tells everyone.
That is not true. The orbital periods were determined long ago. For all of the planets according to Kepler's laws in the 17th, 18th, and 19th century, long before NASA was around.
What it is.
I'm actually planning to do a video. I got from our observatory, where I'm almost finishing my master, I got a really old book from 1832 that recorded the positions of some stars in the frankly really weird way that I'm unsure how to convert it to modern coordinates. But I hope that I one day can do a video about it and show that through this almost 200 years the positions have changed, which big surprise, right?
Many of these are factual, right? I'm sure Mercury, Venus, Earth, Mars, the ones that, Jupiter, once you start getting out into, tens of thousands.
Okay, I will cut here because we've reached roughly 15 minutes, and we'll go back and explain the rest of this again with a little presentation. Okay, so here we are back again. I've still up the slides from last part's conclusion, where we said that, well, you haven't given a single statistical process. You have failed to give one phenomenon that isn't explained by globe maths, and, well, all those things. Great, so let's talk about the Saros cycle. Well, the Saros cycle only gives the probable day on which something occurs. I mean, the Saros cycle used to be predicted, used to be there for predicting eclipses, right? And it only gives a probable day. You didn't talk about this. You only talked about duration. But the thing is here that it's purely empirical. It changes very small over thousands of years, and if the changes are long enough or large enough to change the actual day would be many 100,000 years. This is just speculation on my part because I don't know exactly what they use in the Saros cycle, and I frankly am not all that interested. But hundreds and thousands of years are the more optimistic case. I think it would be a lot more than that, probably millions of years, maybe. I don't know. But either way, it's just not conclusion. It's just not a conclusive thing to say that it's always perfectly that time. Well, you made a claim without providing any evidence for it, which is kind of the flatter thing to do here. And it's again not a statistical thing. The moon, I've written it out here. The equatorial diameter is 4 kilometers roughly more than the polar diameter. It's spherical due to gravity. By the way, the 29.5 days are just an average, and the synodic month, which is this period thing, varies by about lengthens due to the moon slowly moving away a couple of centimeters every year, day, some unit, changes by about 0.15 microseconds a year. So no, it's not perfectly 29.5 days every time, which leads me to one of the questions again. Did you actually look this up? Because I don't think you did. You didn't do your own research there, buddy. And again, it's not a statistical thing. Tidal locking is not a coincidence. I have elaborated this previously. You have, if you have a body that is not perfectly spherical, which the moon isn't, the gravitational pull will cause further bulging. It also does this on perfect spheres, by the way. And because this bulge then moves, if it's not tidally locked, this causes the difference in gravitational pull on the far side and on the close side causes a small amount of torque. I talked about this in the last video. This is a well-known phenomenon. Just Google it, tidal locking, and you will find the mechanism behind it. The craters on the moon, they are not equally distributed. That is correct. But this is due to surface differences. The Earth is in the way on one side, and the big reason kind of is Earth's gravity, which, by the way, again, is not a statistical thing. Let's say we have two asteroids coming from opposite sides. One is coming from the Earth side of the moon, and one is coming from the other side. Asteroid 1 here has a good chance of hitting the moon because there's nothing in the way. What else should happen? But asteroid 2 has a very bad chance of hitting the moon because Earth's gravitational field will pull it in, likely, not all the time. There are still, of course, a lot of craters on the close side of the moon, but will likely deflect it. At least there's a chance that something can deflect it, where on the other side it just comes in and hits it. So one side is protected. I say protected here. I should have said more protected than the other side. Of course, there are still asteroids on this side. Orbital periods, by the way. The example he listed is Venus. Venus's orbital period is 224.7 days, roughly. It changes by 50 milliseconds every year, I believe. So, no, not the same. This due to interaction with other gravitational bodies, although this is, of course, an extremely small change within a lifetime. It's tiny. Within the lifetime of one human, this is extremely tiny, right? And it's similar for every other planet or every gravitational body, really, which, by the way, is completely in agreement with the globe model and not statistical in any way. Yeah, so far, part 2, I have devised here from watching half his video, the flat Earth plan of action here. You don't research any of the numbers more than the first Google result. You make claims about this nature, and this time, oh, it's perfect, which you did not supply any evidence for. You say, oh, it's impossible in our model. We obviously are dumb, and with that, it is kind of implicit that well, the Earth is flat. That's kind of the, because our model is so wrong, can't be our model, when really you should maybe have researched our model to begin with, because the first step already is where your plan fails. Please research those things. Really, I beg you, please do. I will, of course, have a look at the other, the remainder of the video, but not today. And with that, I wish you a very nice day. I hope you enjoyed it. If you did, maybe consider leaving a like. If you did not, maybe considering subscribing. And yeah, I will see you in the next video. Until then, have a nice time. Goodbye.